turn off this guy. So we've wrote our first mathematical model for a simple epidemic where individuals can be either susceptible or infectious. Now, this is one of the few models, I guess maybe it's the only one, that you can actually solve the equations. Okay? The other models, all of them, the other models, you will need to use different methods. I call numerical methods. And you have classes, you have 4 classes of numerical methods in the school. So this is the SIS model. And so now there comes a small piece of algebra and some manipulations, but which will take us to a very simple form for this equation. So first of all, remember, the population is constant, equal to n. Therefore, S and I are not independent. They have to sum to give the value n. Okay? Therefore, I can just say S is n minus I. Substitute in the equation, and then I have an equation only for I, which is S is by this later. Okay? Let's do this. If you do this, di dt will be di dt here is equal to, you have beta times I divided by n times S is equal to n minus I, okay, minus gamma I. So this can be a little bit simplified by beta times I, 1 minus I over n, minus gamma I, which is not anymore a system of ordinary differential equations. It is single differential equations, which happens to be solvable. In order to look for the solvability of this, let us just do some small steps here. You multiply things here, beta times I minus beta I squared over n minus gamma I. So I'm just opening this parenthesis. Okay? And now I have the I term is multiplied by beta minus mu, minus gamma. Sorry, beta minus gamma. And then you can write this in this following way. 1 minus beta I divided by n times beta minus gamma. Okay? So this is just rearranging this equation, but this equation can be written in the following way. di dt, it's some parameter r times I, 1 minus, I have 1 beta too much here, okay? 1 minus some I divided by some k, where r is beta minus gamma, and k is n times 1 minus gamma over beta. Okay? This is an equation which can be solved. It's called the logistic equation. But we are not so much interested in seeing the solution. We want just the plot of the solution. It's much easier. Okay? So this gives you the following plot. Over time, You start at a certain number of initial infectives, which usually we will consider to be very close to 0. And then you have here one value, that's the value of k, and then your number of infectives increases, and then after long enough time, this number goes to a constant, which is the constant k, which is given by that. Given that r is positive. So if r positive. Okay. Now, r positive, if r is negative, that means that the initial population will decrease. You have no epidemic at all. Okay. So r positive means that beta is bigger than gamma, which you can rephrase as beta over gamma bigger than 1. And this guy here is usually called R0, which is beta over gamma. This is called the basic reproduction number of this disease in this population. And it gives you a threshold value, meaning what? Meaning that if this is bigger than 1, I have an epidemic. And if this is smaller than 1, I don't have an epidemic. And this will be happening again and again with all kinds of models. And we will discuss R0 extensively, because at this point, this is still, I think that you cannot, it's difficult to measure. Okay? Beta is measurable. Gamma is better. Okay? But actually, this gives you already some intuition. So the larger beta, the more infectious is the disease. It is a highly infectious disease, has a larger value of beta. Okay? Because beta is connected to the probability of infection. So larger beta, higher probability of infection, means also larger R0, and it's more likely that this is bigger than 1 for a highly infectious disease. So if you have a disease, for instance, that has evolutionary processes going on, so if the infectivity, which can be, infectivity can be divided in susceptibility plus transmissibility. It's not the case to discuss this here, but the infectivity increases. For instance, you have a new strain, higher infectivity. That means that R0 is increasing. Okay? And remember, gamma has a meaning. 1 over gamma is mean. It's the mean period of infection. Okay? So 1 over gamma, if you have a disease that is infective for a longer time, then it means that 1 over gamma is big. It's more likely that you have R0 bigger than 1, which means you have a long infectivity time, you have more chance to infect others. Okay? So it makes sense. But this model, but this is very particular to this model, it has not only a condition for the existence of an epidemic, it also has a full solution. And the full solution in this model says that after some initial increase, and you can see that there will be an actually exponential increase, then you settle down to a constant number of infectives. What is this? This is an endemic state. So in this model, the epidemic does not burn out. It does not go away. It settles to an endemic state. Okay? It stays in the population. Okay? Oh, this is our good friend, R0, and we will be working a lot with this. Just so you can also pay attention that K is N 1 minus, so this is N 1 minus 1 over R0. Okay. I'm using this notation for R0. And by the way, there are people that also call it R0. Okay. But I use R0. I use this double R here because I want to distinguish this from a guy that will appear in the next discussion, which is the number of recovered people in a population. It's also R, so I'm using this one. Okay. So if R0 is bigger than 1, a small initial introduction of an infectious population, so 1, 2, 3, 5 individuals, will generate an epidemic. It will settle to an endemic state. Okay. Okay. So for those of more mathematical interest, so this equation here is very easy to study because this equation has 2 fixed points. Points are values of I such that di dt is equal to 0. So if di dt is equal to 0, then either I is equal to 0 or k is equal to 0. And then you can show that if R0 is bigger than 1, the state with disease-free I equal to 0, if it is perturbed by an introduction of small number of infective, it is unstable. You don't go back to I equal to 0. You will drift away from the fixed point I equal to 0, and you will end up at the fixed point I equal to k. Now, the fixed point I equal to k, which makes this guy here 0, can be shown to be a stable fixed point if R0 is bigger than 1. What is a stable fixed point? You have a certain number of individuals that corresponds to this fixed point. I go there and I perturb this artificially. What will happen? So if it's stable, means that the number of infected will go back to this value k. This is stability in loose words. You can define this better mathematically. So this is just some jargon from fixed points and stable fixed points that can be used in many contexts. Okay. Okay. So now, nice. At this point, R0 has been introduced as a variable that gives you a threshold. And this is a pretty mathematical introduction. I have an equation, and I want to know if initial population of infected will increase or not. Okay? So it's at this point, it's a mathematical okay? So can we do better with it? Can we give some epidemiological interpretation for R0? And yes, we can. So now, let us think about the following problem. One is the number of secondary cases that one primary infected case will generate over the course of the disease. So I am infected. I have infection, say, 5 days. How many people will I infect? And then you look for all the populations, you look for the average of that. Okay? So this is what we want to know. So the number of secondary cases has somehow to be proportional to what? Well, to the time the person stays infective. Period of infection. The time the person stays infective, it is, if you have a longer infection, you have more probability to pass this. I'm not taking into account public health measures, and we will discuss this, but you can quarantine people and effectively to, make them separated from the population. Then somehow this should be the number of contacts also. So more contacts, higher probability of infection. Then probability of infection given a contact. Again, it's the probability that the contacted person is susceptible, and I'm saying that it's just a fraction of susceptibles in the population, times some probability of infection, P. Right? Given a contact between a susceptible and infected, what's the probability of infection? So now this looks very much like the other things I have discussed, and this is actually the same thing. So this here is what we called K before, okay? And this is period of infection. So the mean period of infection is 1 over gamma. Oh, nice, 1 over gamma. Times. This is the K times S over N times P, and I put this here, and this was our beta. So this is 1, it's beta over gamma times S over N. Now, I should have been more precise with my question. I want to know the number of secondary cases which are created by a primary cases at the beginning of the epidemic, at the very beginning. And at the very beginning, the population S is more or less equal to N. Okay? You have a population of 1 million, you have introduced 3 infective guys. So S over N is very close to 1. Okay? So this guy goes to 1. And this is our friend R0. So R0 is the number of secondary cases that a primary case will create. Does it have some importance that we have this interpretation, or could we just maybe stay with this interpretation? So you could now raise the question that you want to know R0. How do you know R0? And this is not so much so easy. So one way is if you have really a very initial phase, and you can trace the contacts of the initial infective individuals. Okay, so there was it had been tried with COVID-19, with SARS-CoV-2, in the very beginning in China, because once it gets around, your contact tracing, just getting to know who you contacted and who you infected and so on, it becomes impossible. But at the very beginning, it's very small number of cases, and then in the case of COVID, this had to do a lot with in-house domestic transmissions and so on. You could trace better how many infectious people were generated from one infected person. So this could be, but this is rarely the case. This is suppose that you have a surveillance system, which is almost a big brother. I mean, it's like you can go and find all the cases. Okay, so most of the time you won't have that. Okay? So then you say, okay, but I could look at this here, and let me say again at this equation. Let's go for here. Let's look at this second equation. If I say S over N it's more or less equal to 1. At the very beginning, I have di dt is equal to beta times I over n. No, not over n, because it's S over n, minus gamma I, which is equal to beta. Let me see the best way to write this in order not to make a confusion. It is let me see what so this is beta minus gamma, obviously, times I. Okay, so which is equal to gamma times R0 times I. Okay, and no, wrong. R0 minus 1 times I. So this equation is a linear equation, and we know that the solution to this equation, I, is proportional with to e to gamma R0 minus 1 times t. So there's R0 and gamma here. Okay. Now, you could say, now I will take the epidemic curve, look at the beginning, it's an exponential, and I just find the parameter of the exponential, and it will give me this thing. So, stop. Now, guys, what do you think? Can I measure I? Can I measure from epidemic data? So I is the number of what is I? It's the number, in fact, it's the number of active infected people. Can you measure this? How would you devise a way of measuring this? You could test. You have to test all the population. Yeah, this is the number of new infected guys, not the total number of infected guys. And that's the point. You cannot measure I. And you want not only to measure I, you want to measure I over time. Testing people, you test people every day, all the population, so it's not feasible. But what you have is maybe you can, so that will depend on the disease. Okay, there are many problems of that. But you can have the what is called the incidence, the number of new cases per day, or per unit time, if you want, day, weeks. Okay, so this is easier. Depends on your surveillance system. Huh? So, what happened, for instance, with COVID-19? Can you know the number of new cases over the last day or the last week? No. Why? Because people get either asymptomatic or what's called oligosymptomatic, or just stay one day at home. They don't have to go to the doctor. At the very beginning, everybody got to the doctor because people were very afraid, and it was actually cause to be afraid. But now, you could say, okay, I can find a variable that will be connected to the actual incidence. It's just the number of severe cases. And the number of severe cases is the guys that go to the hospital and get admitted at the hospital. And this is easier to survey. You just need the hospitals to make the notification. Okay? So I think probably Marcelo will tell you all the horrors of putting this into practice, because, you know, as I say, it's just that you have just to make the notification. Okay? But yeah, I mean, we did it three weeks to take the notification. Okay? So, okay. But anyhow, so in principle, you could have, for instance, in COVID, the incidence. Okay? So incidence is much more feasible in general than total number of active infective cases. Okay? So, but where is the incidence here? I have and I have no incidence. Okay? But the number of new cases per unit time is just disguise here. Okay? This is the number of new cases per unit time that flows into the infected period. So, if I call J of T the incidence, in the initial phase, J of T will be proportional to what? To beta, but then you have S divided by n approximately equal to 1. So it is proportional to I, beta times I, proportional to I, which is growing exponentially of gamma times rho 0, R0 minus 1 over T. Okay? At the initial phase, do not confuse that this is growing initially with this exponential, which happens to be the same exponential as the function I. Over the course of this epidemic, this won't be anymore true. Okay? But this happened only because S is equal approximately to S over I is equal to 1. Okay? So that won't happen all the time. So next class we will also discuss this. So now this would be easier to estimate. To fit, I have a number of new cases per day, which is growing exponentially. But yeah, guess what? If I just grow this, that's really fantasy, okay? But what you have, it's a whole fluctuation around this, and then this will be just kind of mean over several days. So the rolling mean over 1 week, for instance. So yeah, people use very usually people use weeks and not days. Can you give me one intuitive reason that it's better to use weeks than days? So I want to make a plot of I over T on the time. So every point could be 1 day, or could be also every point could be the accumulated cases of a certain week. Why do people sometimes, and there's even something that's called the epidemiological weeks. So it's a kind of standardization of weeks of the year, so they have some numbers, and then you can compare over countries and so on. So why weeks? There's fluctuations. So first, there could be a daily fluctuation, but what else? So the time, no, I mean the number of new cases is not connected to the time of infection. So not so much that. So it's much more practical thing. It's a data thing, yeah. Yeah, notification. People do not do notification on Sundays. And Saturday afternoons also. So what you get is it's a very small number on Saturdays and a big number on Mondays. So because not all days of the week are the same from the notification point of view, but all weeks are the same. Well, okay, Christmas week or something, there are some bumps, okay? So the idea is that in order to, this corresponds to taking the rolling mean of taking a 7 days mean, okay? So that's just the practical. Okay? So this will be fluctuating and it will be increasing, and then you know all the drama of exponential growth, people die on the streets and so on, blah, blah, blah. Okay, Now, but our problem is more mathematical. We want R0. And so what's the growth factor? The growth factor, I can call this R, let's say, e to RT. So you can fit an exponential here, which is nice exponential, and find the growth factor R. Okay? They can find that. One easy way to do is to make a logarithmic scale here. An exponential on a logarithmic scale is a line. So R is only the inclination of your line. It's not difficult to do. You can do this even with all the fluctuations and so on. Very good. But R is not R0. So R is equal to gamma times R0 minus 1. Okay? Now, therefore, from the epidemic curve, an incidence curve, you cannot calculate exactly R0. You need more information, which is, in this case, gamma. This will be true in all of other cases also. So there's a whole difficulty in calculating R0 for actual epidemics. And even with the models here, okay, this one is very easy because it had only one parameter, which is gamma. Okay? And then you summarize the mean time of infection, mean period of infection. So I more or less know gamma, and then, well, I have measured this guy, I know gamma, then I know R0. Okay? Yeah, fair enough. Okay, for simple epidemics. Okay? So, but the point is, the incidence curve gives you a growth rate, and the growth rate is not R0. It contains R0 and other parameters. In our model, it's just one parameter, which is gamma, and therefore it's easy. Okay, but could be a little bit different in more complex cases. Okay? So, great. I didn't. J is proportional to e to RT, which is proportional. There's a proportionality constant, which is not important for us. Gamma R0 minus 1 times T. Okay? Here it's J. Okay. Yeah, that's J. It's not I. So I have seen in some conference, more mathematical conferences, the people that use I as if it were G. That's a real problem, right? One real problem about the incidence is also that you have the delay of notification. Okay, this depends on your public health surveillance system, and this depends on, in Brazil, this depends on the states and on the politician that rules the state or whatever. But for instance, I would say still relying on COVID and severe cases of COVID, I can remember well that there was a daily report of cases, of severe cases in Germany. Okay? It had a delay of 3 days. Okay? So 3 days is still okay. You can wait 3 days to get the result. Okay? So it's not bad. But what you have here, and Marcelo probably talk about now testing and so on, is that you have delays, and they have a distribution of delays. Some hospitals just go quickly. They will make the reports because they have a person that is there to do this. Take, for instance, a specialized infectious disease hospital like Emilio Ribas here. And then maybe there are other hospitals that the nurse that makes the notification. The nurse is overwhelmed by the number of cases. They cannot do the so there is a place, And then in order to make this calculation, you will have to take all of this problem, the data problem, into account. This is just to make you have a window to what will come in the afternoon. Things are nice here, and what we are doing is to develop the concepts. But in order to calculate things, you need statistics and you need more things than just this. Okay. So now we want to give a further step and write down a new model. But now I want to discuss all the story about how this beta came to be, what's the meaning of gammas and so on, because this will be the same thing. And the model that we want to discuss is a model that has a new compartment, which is the recovered people. So recovered people, so we have susceptible, infective, and recovered people. Okay? So I will erase everything because this, and now I want the whole blackboard for the new model. Oh, it's a lot. So nice, all the blackboard for the new model. So which will be the model which has susceptibles, infective, and you become infective through the contact from I with S, and then you go from here to a recovered population. So the population now has 3 classes: recovered, infective, and susceptible. And I will do, so we have to know what's the fate of the people that are recovered. Will they stay immune from the disease? Will they stay sometime immune and then lose immunity? Or will they just get susceptible very, very quickly? So our model, which is the SIR model, at this time, at this moment, will take immunity to be permanent. Right? Actually, do you think there is such a thing in the world? Yeah. Give me an example of a disease that gives you lifelong immunity. Rubella, yes. Rubella in English, I don't know. Ah, okay. I mean, these translations I never know exactly. More? What more? Yellow fever gives you lifelong immunity? Kashumba, how is kashumba in English? Mumps. I'm not sure mumps, I think yes. But that is one that is the most famous, is measles. Right? Measles. Okay, you get lifelong immunity to measles. And you have a vaccine for measles, which also gives you, I mean, it's not 100% vaccine. It's a 97% vaccine. So if you are the unlucky guy that is in the 3%, maybe you got partial immunity only, but most of the time you become immune, and you don't have to take it again. Yeah, it's the same time as if you had measles. For instance, I'm an older guy, and I had measles at the time. People had measles as children. Okay? So I'm immune to it. Okay? So, but the many other cases that is not the case. You have immunity, then you have people flowing back to the susceptible cases in a certain rate. So then you will have a period of immunity, as you have a period of infectiousness. Then you will have a period of immunity, and after this period, you flow back to S, and then everything starts again, and all the results that I will derive here won't be any more true, okay? Because if in this model you have S that can become infected and recovered and get immune forever, there's no flow back to S. So S can only decrease, okay? Can only decrease. Unless you take into account demography, but we are not taking into account demography. Demography means people that are given birth and people that are dying. Okay? So now, with the same arguments that I gave you before, you will probably be okay with I writing down the model like this. So this is the same thing that we had before, just the same thing. Okay? But there's no inflow here. It's only outflow. Okay? Then you have the IDT is equal to beta Si over n minus, so I will use, minus gamma I. So 1 over gamma is still the same thing. It's the number of, it's 1 over gamma is the mean infectious period. And then instead of going here, it goes to this compartment, the RDT, which is an compartment which has only a positive influx. People don't, there's no outgoing which could go, I don't know, here. Okay? So that's the model. Okay? So you are seeing that the rationale to build models is more or less the same. And different models can be built as long as you know what are the important ingredients into your model. Okay? So, and this is an important thing, but when you sometimes talk to people who have more biological background or public health background, sometimes you have people that want to have all the details, and this is complicated for modeling, okay? So you could say, no, but maybe there's a very small rate of people that don't get recovered. So then you have to decide, is this important for you or not, okay? So building new models, you have to have clear what are the new biological facts that they point in the model. For instance, you could have a latency period. So people get infected, but they are not infectious. So they have a latency period. There are people that will have a new class with latency people in latency, and people that are infectious. And then you have all the kind of things. There are people that are infectious before being that are infectious, but without symptoms, and then they develop symptoms. You can put all of this into models by putting more and more classes and looking for the fluxes between the classes. That's the way that you can play with that. But to do a sensible thing, you have to know what are the important biological facts that you want to take into account, and what are effects that are not so important. Okay? So you have the model. And now, this model is not like the other one that I can write down the equation, the solution. Okay? So let me just make a point, a mathematical point. The fact that I cannot write down the solution for S, I, and R as function of time does not mean that the solution does not exist. The solution exists. And a physicist would usually say, but I cannot write down this solution in terms of known functions. What are known functions? Trigonometric functions, exponential, logarithm, polynomials, rational functions. That's things to know. And a mathematician would raise a hand saying, that's complete bullshit. Why? Because your definition depends on what you know. which is a psychological or educational issue. It's not a mathematical issue. Okay, so that's a good message for physicists in many areas. The solution exists. You can get the plot of the solution because you can do numerical methods, a lot of things, and so on. But and this is enough for us. So being able to write down in terms of known function is not a mathematical fact. That is actually, but obviously it's a practical fact that if you can do it as we did with this SIS model, it simplifies your life because it's you get new things in terms of things that you already knew. Okay? So now I want to study the epidemic threshold. And the epidemic threshold is at when S over N is close to 1, so at the very beginning of the term. At the very beginning, R is 0. Okay? There's no recovered if you don't have infective. And the number of infective is very small. There's the introduction of, in ecological terms, you would say that the I is able to invade the population of susceptibles. It's like a biological invasion. And so you want to know when this is approximately true, if I introduce a number of infectives, will the number of infectives grow or not? Or will it just decay? Then you have just to look for this equation here. Yeah? So di dt is equal to beta I minus gamma I, which is equal to beta minus gamma times I, which is the same equation I had before. Nothing changed, okay? Because what changes is this guy now goes here instead of going here, but at the initial phase, it's actually the same thing. Okay? And then this is equal to, if you want, gamma R0 minus 1 times I. Therefore, R0 equal to beta over gamma bigger than 1. You have epidemic. And all the interpretations that we gave for R0 are still valid. Okay? So is there something more funny about this? I mean, it seems it's so closely related to the first one. So that is actually a new word. And why? So the epidemic threshold is it depends on beta and gamma, or if you want on gamma and R0, it's the same thing. But now you want to know what happens as the epidemic goes on. Remember, the other cases, you actually went to a stable number of infectious individuals and you have an endemic state. Now here, things start to change. Why? When in the previous model, these guys went up here, you have a replenishment of the susceptible pool, which could give you an equilibrium here. But as these guys now go to this, and this doesn't go back to this one, S can only decrease because it's negative and all these guys are positive. So it can only decrease. And if this decreases, then this S over N, we are not anymore in this approximation. This S over N can become smaller, 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 and this term can become bigger than this one, and the number of infectious guys can start to decrease, which has not been the case before. Okay? So as S goes smaller and smaller, the importance of this term relative to this term is smaller and smaller. So this is a negative term, this is a positive term. The negative term can overcome the other one. So, now, this is nice. Then let me just give you a fact. So, as Renato Coutinho will show you this afternoon and tomorrow and Sunday, it is possible to actually get a solution of this equation by methods which are called numerical methods. Numerical methods won't give you the function, but will give you the solution as a table, which you can plot. Okay? So, then you please believe me that if you do this, or if you want, you can write a small code in your preferred programming language, like Python, R, or whatever. It won't be even 10 lines in order to get this plot here. Okay? And you have I of t. You start with a small portion here. You will increase, because the initial phase is exponentially increase, exactly this that you had before. You will increase. But at a certain point, you know, this term balances this one, and the IDT at a certain point will be 0. And then it will be negative. It will go down here. Okay? So you see I'm not good at drawing, actually. So this looks like symmetric, yes? But it is not. Okay? So better draw. Let me do something, a better job. It's better, much better. Okay, it's not symmetric. Why I am saying it's not symmetric? Because, you know, people, we are doing modeling with considering, that's kind of what people call mechanistic modeling, in the sense that we are trying to see the mechanisms, the main mechanisms that give you disease recovery and so on, and put this at a populational level. And but there are people that don't like so much, and there are people that there's a famous case of people that argue that approximately this is kind of a Gaussian, a symmetric Gaussian thing. Okay? This led, and I think this has a name. I think it's FAR law, FAR, F-A-R-R, but I'm not sure. Maybe FAR, the guy has nothing to do with it. But what happened is that in the beginning of the 80s, people applied this to data of HIV/AIDS and discovered that there will be only some 100,000 deaths, and then it will go away, which completely wrong. Completely wrong. So don't be fooled that this is symmetrical. Okay? In some cases, it will be closer to symmetrical. Yeah, could be. But it is not, in general. Okay? So, now you could also draw a different plot, which is a plot. This is a more conceptually, a little bit more involved. It is, I take S over N and I over N. And I want to plot on this plot, which is called a parametric plot, the solutions. So every solution has a value of S, of I, and R. I'm forgetting R because R is not connected to these equations here. It is just, R could be a repository of this. Okay? It's just counting. So this here, this is a system of two differential equations. It's closed. And so your initial conditions, in general, will lie on because you have N is equal to S plus I plus R, and N is constant, a constant population. At the beginning, R is 0. So any initial condition has to be on that line, okay, which is the line given by I is equal to N minus S. Okay? And then consider R0 greater than 1. Then you can put here 1 over R0 if you want. And then if you start here, so you will grow, and after some time, you will go back. You will go to 0. This guy here goes to 0. Okay? And then other ones here that will do this, and so on. Now, at the end of the epidemic, at the end, I of time, at the end is time infinity, okay? Is 0. This is the epidemic then burns out. I'm not considering birth and death process. It's a closed population, okay? So, this is at the end. Now, what about S and the number of recovered? Can I get something about them? So, in particular, I want to know if at time infinity, will I have S equal to 0 and R equal to N? Or will there be a number of susceptibles remaining in the population after the infection burnt out, after the end of the epidemic? Right? So that's a good question. Okay? Will the epidemic infect everyone of the population, or will there be people that will escape before? Will they escape? And I mean, after the end of the epidemic, will there be a remaining population of susceptibles? Okay, so the number of people that got infected in an epidemic is called the total size of the epidemic. Okay, and I can rephrase what my question here is to know. In this SIR model, the total size of the epidemic, is it equal to N or is it smaller than N? Okay? If it's equal to N, everybody was affected because everybody got. Okay? If it's smaller than N, then some people escape it. Okay? So now, in this case here, you can do a mathematical manipulation, which is kind of, it is correct, but it's a little bit ugly. But, okay, you can close your eyes if you are very sensible. You can do the following. You take this equation here and divide it by this equation here. Okay? Divide one equation by the other. Ugly, yeah? Okay, so ds dt divided by dr dt, the dt cancels and give me ds dr. This can be done, actually, mathematically, because you have regularity of the solutions and of this function. So it is allowed to do this, okay? But you should have proved this before, okay? It's not the case here, okay? So, and then here, this term divided by this term will give you beta over gamma, our old friend, 0, and then I will cancel. Okay? So this will give you the minus sign. There's the beta, and there's the gamma that is dividing it, which is R0, times what? The I cancelled, then you have S over N. So looking now at the number of susceptibles as a function of recovered, we have a linear equation. Miracle. We can solve the equation. Okay? So S as a function of R is equal to some constant, E to minus R0 by R over N. So pay attention, I use this different symbol for R0, not to confuse with this R. This R is the number for recovered. This one is the basic predicted number. Okay. So, okay, then the value at t equals to 0, okay, the value of S at t equals 0, R is 0, because at the beginning of the infection, the infectious process, there are no recovered, because you have only some very small number of infective, and the rest is susceptible. So S at time 0 is just equal to n, okay? Which implies that S over n, so this means that 0 here, that C is equal to n, okay? So S over n is equal to E to minus R0 times R. Now we want to look, so this is nice, simple equation. Now at time t equal to infinity. So after R over n, yeah, right, okay. Yeah, everything is on fractions. Thank you. So at time t equal to infinity, we know that I is 0. Therefore, n is equal to S infinity plus R infinity. Okay? So this says here that 1 minus R infinity over n, so I substitute S here, okay, is equal to E to minus R0 times R over n, okay, at infinity. Okay? R infinity. So I calculated this solution at time infinity and made use of the fact that at I is equal to 0 in infinity time, so S plus R is equal to n, I can write S in terms of R. And I get this. What is this? This is not any more differential equation. It is an equation for R0. We are supposing that for R0 over n, I mean the proportion of R0. And this depends only on R0, on the basic reproductive number. So this gives you an equation for the number of recovered people at the end of the epidemic. And the number of recovered people at the end of the epidemic is equal to the people that got infected, that got recovered later. Therefore, this is the total size of the epidemic. It's the number of people that had been affected, that have been infectious at certain time and then recovered. So this is an equation, but it is a transcendental equation, okay? So you can use your favorite mathematical apparatus by numerically integrating this for many values of R0. It can be, I have here, I can say I have a certain function here. Here I have a decaying exponential that has to be equal to a linear line here. And then when they cross, then you have the solution. And so but this means that this can be calculated, okay? Again, it's not doing by known functions, okay? But I hope I've convinced you that you don't care anymore if you know the functions. And then what you do at the end is you make a plot. And what is interesting here is this equation for R0 over n has only one parameter, which is R0. So I can do the following plot, R0 over n, R infinity over n divided by R0. Okay, so the total size of epidemic, total size, Then you have a threshold value, which is R0 equal to 1. And if R0 is smaller than 1, the total size of the epidemic is 0, because there's no epidemic if R0 is smaller than 1. Okay. Remember, R0 bigger than 1 was the condition for the existence of an epidemic. Therefore, in order to talk about total size of an epidemic, I need R0 to be bigger than 1, but otherwise I don't have even an epidemic. And this here is something like that. And it gets very close to 1. Okay. So, the larger R0, the bigger the total size of the epidemic. Makes sense. R0 as a measure, it depends, for instance, on the infectivity. So a very infectious, easily transmittable disease will create more infected people. Okay? Therefore, the total size of the epidemic will be larger. Okay? So, and this is tells me that I am very happy and that not everybody got infected at the end. And now we remember the first part of our historical review, that had a lot of epidemics affect all the population. For instance, the influenza epidemic in 1918 affected 1/3 of the world, not the whole world. Okay? There are geographical things involved, but anyhow. And even also other ones that we have talked about, they don't affect everybody. Okay? So in this case, this comes from the fact that the people are lifelong immune. Lifelong immunity is what makes this happen here. Okay? Now, you could be wondering, so now, before that, so what's the importance of this exercise, calculating the total size of the epidemic? What is R0? R0 is the initial growth rate, or it is the number of secondary cases that one primary case creates over the course of the disease for this person, and it's the average of this thing at the very beginning of the epidemic. Or in mathematical terms, R0 was connected to the increase of exponential increase at the beginning. Yes? So it can be determined by the beginning. But if this model is a good model, you get the total size of the epidemic from a parameter that has been calculated at the beginning of the epidemic. Okay? So it's a kind of tally connection between the beginning and the end. But obviously, this depends. That model has to be true. Okay? But there's a connection between R0 calculated at time t equal to 0 to the total size of the epidemic. Okay? This has profound implications. Because this means that, given this curve, that you can do a rough initial assessment of the danger that a new epidemic poses. For instance, if it's an emerging case, by knowing R0, you can say that the proportion of the population that will be affected by this epidemic. Okay? So this is important. Okay? Now, so far so good, but you have to be also careful. Okay? But this strongly relies on your model. You can't, it happens, however, that for more involved problems, which are epidemics that burn out, not epidemics that become endemic. But if they burns out, because if it becomes endemic, there's no sense of total population, total epidemic size, because the total epidemic size is after it finished, then what's the number of people that got infected? But if it does not go to have an end, it goes to an epidemic state, endemic state, then obviously there's no sense to talk about total size of the epidemic in this formulation, at least. So, but people have shown that even more complicated models can give you a relation between R0 and calculated at the beginning with the total population, total epidemic size. Okay? So, this is what, if you do this assessment, I calculate R0, say it's an emergent disease, like COVID-19. I calculate R0 at the beginning. I have an estimative. For instance, R0 for COVID at the beginning, means before we had variants, it's kind of 2.5. Okay? So R0 has no dimensions, it's a number. Yeah? Okay? So 2.5, which would mean a very high number here of infected people. Right? I can't remember now, but it's more than 80%. So, then you could suppose a certain fatality rate. You could estimate how many people would die from that. And then you can scare your president. It depends on your president, prime minister maybe. So actually this happened, and this was a matter of a long debate, because the group of an Imperial College in London made this kind of exercise. It's not an SIR simple model, it's a much more complicated model. But it came to the point that there was the worst case scenario when nobody takes any preventive action. You would have 2 million of people dead in US, in the United States, and I think 800,000 in UK. So this actually moved at the time the Prime Minister of UK, Boris Johnson, to pursue a stay-home mandate. Okay. So now there had been a strong debate about this. Why? At first, okay, R0 has been more or less well estimated, but in the case fatality rate at the very beginning, it's also difficult to calculate, okay, because you don't know actually, because usually epidemiologists make a distinction between it's called infection fatality rate and case fatality rate. And so case is sometimes not a synonym of infection. So there are people that have no symptoms, and then they are not counted as a case because they completely disappear from any surveillance system because they don't have anything. So, so it is difficult to know. So you can have a model, but if you don't know the proportion of asymptomatic people, okay, it is very difficult to know the actual estimate for the total number of dead people, right? Because you could have a much smaller number than 2 million if many of the cases were just asymptomatic. Okay? So there are difficulties in doing this. There have been a debate on that. And then there's also a debate about public communication. And pretty much one problem with the Imperial College think was also at communication. So, okay, so they communicated, that's the number. And actually, this moves people to take action. Okay, I don't want to have 2 million people dead in my country. Okay, so not all people take, not all presidents take action, but anyhow. So, and then obviously your calculation becomes wrong by definition because people take action. Okay, so that had been criticized also, and that it is in the report of the Imperial College that this is the worst case scenario. If you don't do anything, then you have that get this. It's not so bad. The US has 1 million with all the measures that have been taken. Okay, so it's not so bad. Okay, it's instead of 2, it's 1. But there have been people using masks, people staying at home, people getting vaccinated, and so on, which is not in the model at all. Okay, so but this kind of communication, that's a problem. You write it. It's the worst case scenario. If you don't do anything, that will happen. But then you go on and press releases or the media system from Imperial College, and it omits just this. I have 2 million. And then people get scared, and then you don't have 2 million, and people say, this guy just are not good scientists. Right? So this is difficult in modeling results or to public policies. It's not trivial, right? So, just to finish, and we are talking all the time about R0, but any of you can have any idea of the value of R0 for some diseases, except for COVID, which I told you that's 2.5. So, any idea? So what's a very infectious disease? Infectious disease. One that's very, very transmissible. No, ours is almost COVID, so yeah, it is infectious. But if you're looking back in the history, and influenza, yeah. The problem with common flu and influenza is that they have so many strains that all of this is difficult to apply. Yeah? So it's as if you had every year some. So measles. Measles has, let's say a guess. It's very effective. So I want your guesses. Now, you just say a number, even if it's 10. There's 10. Who gives more or gives less? 8. 0. No, cannot be smaller than 1. Measles. Measles is very effective. 2.5. More than COVID. No, measles is an epidemic. It has R0 bigger than 1. I mean, now it's not because people are... what I mean, measles before existence of vaccines, okay? Before the existence of vaccines, not now. And now there's no measles. I mean, there's measles, but it's very small number. So, measles has 16. Yeah. 16, which gives you practically all the population got the we will in the next class calculate the mean age of infection, okay, which will result to be small. So it's actually a child disease, but it's very, very infective. And most people of my age will remember that all your colleagues had measles. So that's a very big case. Next class, we will also say, look, the relation between R0 and the number of people that you have to vaccinate in order to have immune population. And measles will have to vaccinate like 97% of the population. So it's very difficult. So now, smallpox, which I told you about today, is like 6. Polio is like 7. Dengue depends on environmental things. There's a value that 0.5, but I guess this depends pretty much on the environment. Okay, so that will not be intrinsic to the population. Then the cholera has been measured recently in Zimbabwe, which is, you remember there was a new strain of cholera, which is mild cholera. So it was 2.7. And we recently, I don't know, but you are a specialist on Ebola, yeah? You used to be, at least, at a certain point. Can you remember R0 for Ebola? The point about Ebola is that it's the case fatality rate, the case fatality rate is so high that it doesn't get so much transmission. So it's auto-regulated, but I don't know.
And also there's one thing about Ebola that usually, so depending on the culture of the population that is infected, you have full transmission from direct contact with the living person that is infected. But also you have a lot of infections that are due to the interaction of the cadaver, the deceased one, due to funeral practices. So how different people perform their burial practices affects the possibility. Because the person that dies with Ebola still has a very, very high viral load. So it's infection, even after 2 days. So what happens is, then you get, if you do the model, taking into account not only live individual, infected individual, but also recently deceased people, you can then attribute R0 for those 2 types of infection types, from living individuals and also through interactions of deceased. And what the model shows is that from interaction with the deceased body, then the R0 is much, much higher. The activity is extremely high. And also the contact also rate is also high. And a lot of individuals interact with the same disease. So
Yeah. Yeah. So at least you would have a compartment with deceased people. Yeah. And this usually deceased people is a compartment that has no interactions in most of the cases, but in this case it could have an interaction of fueling new cases. Yeah. Okay. So any other questions or comments? Yeah. The second graph. So this is what called a phase portrait in physics. So for every moment of time, you have a value for S and for I. So for every moment of time, I can plot here the value of S and the value of I. And therefore, the solution will be a curve. As time goes on, S has some variation. I has a variation also. So it will increase and then decrease. And so this is what we call a trajectory in this plot. Okay? This is the line of initial conditions. Why? Initially, you have N is equal to S plus I plus R, but initially R is 0. So this is just the line where you say I is equal to N minus S. Okay? And then here, S will always decrease, because in this model, S always decreases. But the number of infectious people can increase and then decrease. Okay? And then at a certain point, it goes to 0. And they have a lot of points here. So the end state depends on the initial state in this case. So that's a little bit more tricky. That analysis of a simple analysis of fixed points here will be the generic case, which is not so nice to study. So, yeah, anything else? So, one more question, at least. General comment also. Hmm? Hmm?
Why is it important to estimate S and R?
So at infinity, time infinity is as after your epidemic died out. Usually, an epidemic dies out in finite time, not in infinite time. But in this model, obviously here we are always taking S and R and I as continuous numbers. Okay? But when they are very small, you have stochastic formulation here. Okay? So there is, this is the time, S infinity, is the time when actually I is equal to 0. And I being equal to 0, then I do all these calculations, but R infinity is important. Why? How do you become a recovered person? You have been infected, okay? So, and the number of recovered can only increase. People get infected, and this guy is actually counting the number of infectious people, because it comes on all infected after being infectious become R. So when you have no infections anymore, you have a certain number of people that have R, that are recovered, and a certain number of people, and this number is R infinity. Okay? And then you say this is the total size of the population of the epidemic, because epidemic went away. The number of people that had been infected, all of them have recovered, because this is a model with full recovery. Okay? And then you have the total size. Okay? And this here is pretty much step. It's a big derivative, and it goes up very quickly here. Okay? So even with, as I say, R0 equal to 1 means that there's no infection, no epidemic. But R0 equal to 2.5 will already give you a super big epidemic. Okay. Anything else? Yeah. Please a little bit louder. Yeah, it is. Sometimes it's not so easy, because here I use the particular thing that I can divide this by this, and then on this side I only have S. Okay. If I have something else here that already this approach is not so easy, but people have developed things that are involve more complicated linear algebra things, but what the people have given the conditions. So the conditions are, I think, that the recovered are immune for a lifelong immunity. Otherwise, if they lose immunity, you cannot keep track of the number of people that got infected. Okay, so, but well, people have done for more complex models. I can't remember exactly that. I remember there were some matrices and going on around. So. More? So Oh, okay, I think it's lunchtime. So we'll be back here at 2. I think it's Renato first. So numerical methods, and then Marcelo. Today we have a shorter day. We'll have classes until 5:30 only. Okay? And in the week, we will have the group works until 6, but you are allowed to stay if you want to stay more. And then there are some days we have activities at 6. Okay? Thank you. That's it for today.